So let's try to understand now what exactly data we need in order to do this kind of a prediction of that price of an asset in the following, let's say, trading day. And in your site, you have a notebook that is called Time Series Prediction using RNNs. That notebook was borrowed from the Hands-on Machine Learning and Scikit-Learn TensorFlow version 2, edition 2. Edition 3 has a slightly kind of different notebook. And it's kind of an instructive notebook because it is going to be dealing with synthetic data sets. So we will be synthesizing the data that we need in order to do the prediction, and that's why it is a bit more useful for us at this stage. So the important thing to understand is that we will be needing to generate sequences, in fact, thousands of sequences, in a similar way as we had thousands of scalars X that we had dealt when we looked at, let's say, linear regression video, and in a similar way as we had thousands of images when we're dealing with convolutions. Over here, we will actually need to generate many thousands of sequences. So these are examples of these sequences. And for every example, we will need to have a sequence, which is the sequence of 50 values from 0 to 49, as well also the target variable y, which is the x50. Okay, so these are effectively our data set, and now let me sort of write down in a kind of a familiar to us a table that fact. So we still have this x and y table. So for every value we have a sequence. Now I don't want to put necessarily the underbar because that's a sequence of values rather than a vector of some sort, but I'll just overuse the notation. And this is the first example, x followed by another variable, which is a target variable x1. That's one sequence followed by a target variable pair. And this is another one, and so on and so on. So at the end of the day, we will have m of these sequences coupled with their target, the ground truth of the target variable we would like to predict. So in this case, these are the ground truth is the price of the asset in that specific sequence. So what happens after x49, that is your y1 for that sequence. For this sequence, that is your x50. That is for the mth sequence, that's also your x50. Okay, so that is the nature of our trained data set, and this is actually shown over here on the site. Okay, so the initial function, generate time series, is doing just that. It is starting with some form of the number of, it has an arguments as the, let's say, the batch size and the number of steps. And we are generating here 10,000 of those sequences. 7,000 will be assigned to the training data set and 3,000 to the test data set. And we have 50 indices times sequence steps that each sequence consists of. And of course, we're going to have to generate 51 because the last one we're going to be using as our target variable. Okay, that we are trying to create a predictor to predict that target variable. So I hope the code is understood. At the same time, just because the data set is actually synthetic, we actually can see here that the series itself is generated by adding certain sinusoids with certain frequencies, like frequency 1 and frequency 2, and some kind of offsets to control exactly how the additions here. So we have effectively three terms that are, and we're adding some kind of a random noise for at the end of the day to form, if you like, that sequence. Okay, so that is how we will be need to have our data set structured in order for us to learn the structure of this time series. So now that we have seen the structure of the neuron, this is just a single neuron, in the same way as this was just a single neuron, but it's recurrent in nature. So in the same way as we have seen earlier, what we need to do now is, now that we have presented the problem, we will need to understand how we will use this structure, how this structure kind of fits into solving this problem of this X50, the prediction of this time series, the next training day. So let's see. I think it's worthwhile highlighting a couple of things. And by the way, earlier I actually forgot to draw the transfer function or of that tan h. Okay, so this is my tan h of let me call this z, and the tan h is a function that goes from -1 to +1. So this is very similar to what we have seen earlier, and to the sigmoidal function, but obviously it is different because the sigmoid went from 0 to 1. And so because there is a feedback loop over here, what we will do is we'll take this and unroll it in many instances in time in order for us to understand how that data set will be fed into the neuron. Okay, so we will be abstracting out the contents of the previous kind of block diagram into this block. So this block, so the neuron starts with some initial hidden state H0, and it receives the first, so this is just one of the sequences. So this is, let's say, this is a sequence X, I don't know, 1255. All right, so that is, so it receives the 0th element of that sequence in at effectively this is t is equal to 0 to make it a bit more explicit. Then it produces, we'll understand exactly what the output arrow is, but what we will do now is just going to use the output of the neuron, which is the new hidden state H1, and use that as an argument to another transfer to another function that implements the neuron, but this function will now have as input x1. Let me also draw this arrow, which will become important a bit later. This creates h2 together with x2. We're forming h3 and so on. So after a number of steps, we arrive at the point in time where the x49 is going to be fed in, and the y49, y50, it's not y50 but x50. So the h50 is going to be the hidden state. This is obviously going to be my prediction y hat. Okay. So this is my prediction y hat, which is or the one that I was asked to produce. And obviously this prediction is going to be used for driving the mean square error and sort of calculating the mean square error, producing, if you like, a loss, and with the usual kind of a stochastic gradient descent algorithm adjust the trainable parameters of this neuron. Now, we need to be clear so that we understand that physically there is the architecture of the previous block diagram, but here we see a functional representation of that architecture or logical representation of what is happening over multiple instances in time. So physically, at any one instant in time, you have this. and you have the next instance, you have this, next instance, you have this. You never have, all of the elements sort of that you see here. So this is called the unrolled architecture. It's actually very useful for us to draw it this way because in many instances we have to reason about what is happening over multiple instances in time. Okay, so this is the block diagram of how the training will function. Now let's look at this using the Python code. So before we see the implementation of this simple RNN neuron, I think it's worthwhile looking at what it's actually shown here, which is a baseline case. And the baseline kind of tries to answer the following kind of question. Why we had to introduce RNNs? Would the previous architectures be good enough for our purpose? And definitely the answer at this moment in time is positive. Yes, we could have used a fully connected network. And the way that we have used a fully connected network, we will be able to capture in one go in every sequence. We can use a dense layer of let's say 50 elements, 50 with an input size of 50, and an output with just a single neuron. So it is without even the sigmoid. When we will be able to predict the price of the asset. Remember, this is a regression problem, so we don't need the sigmoid. So we just had a dot product, and we could actually use the mean square error to be able to train that simple neuron of just a single neuron, a linear unit, to obtain our prediction. And this is basically what is actually happening here. That whole sequence is fed into that neuron. And of course, we have thousands of sequences that we feed all of them through that kind of training process over a number of epochs. And yes, we are minimizing, if you like, the loss. And we are be able to predict after that model is obtained, finally, when the W star is obtained, our prediction, which is the red over here versus the ground truth over there. Okay, and this thing is working at this point in time. And that is one of the many baselines. Even in convolutional neural networks, we have seen we can actually use use one-dimensional convolution to be able to feed into that convolutional layer, convolutional neuron, the sequence. And there are advantages and, of course, disadvantages with this convolutional approach. One main disadvantage is that in RNNs, we need to be modeling applications. We have variable lengths, both at the input and also at the output. So we'll see those in a future kind of video. But this is both feasible architectures at this point. Okay, it will not be necessarily be feasible for much longer, but at this point they are both feasible. All right, so the simple RNN code is actually shown over here. It is consists of a single neuron, as we have drawn it, that accepts an input shape of none, 1. Okay, this none, 1 means that we are already seeing the advantage of this architecture to accept any number of inputs that we require. These are all scalar inputs, and we are using Adam here. We have not really seen Adam in detail, but it is a cousin of stochastic gradient descent, so you can replace it with stochastic gradient descent, and with at this moment you're not going to see much difference. We will definitely going to train it, as we discussed, with mean square error as the loss, and obtain, if you like, some prediction. And this prediction is actually shown over here. It may not really look quite different than the kind of an earlier prediction, but definitely the mean square error is worse, and maybe the scale is not doing us a favor to highlight this kind of difference. And the reason why the at this moment in time the RNN, the simple RNN neuron that we have here, is performing worse than the sort of linear unit is quite simple if you consider the number of parameters that we have in our implementation. So in our parameters we have we can actually see it over here. So in the kind of a block diagram which I actually have drawn, so mind you, this now does not exist. So it is just a linear unit, what we have in the baseline. And evidently the number of parameters of that linear unit is as large as the number of inputs that we have used. In this case, we have used the whole sequence in one go. So we are talking about 50 parameters here, plus the bias term 51. And in this case, what we have here in the simple neuron, this is a scalar. So the one sample at a time, one scalar at a time is actually coming in. And therefore, we have just 1, 2, 3 parameters here for the simple RNN neuron. And therefore, the number of parameters is quite different. So we are effectively comparing kind of apples and oranges in a sense. To improve the performance of this simple RNN architecture, we need to follow a similar trajectory to what we have seen in the past, that we have followed in the past. In the neural fully connected architectures, we went from a single neuron to a multiplicity of neurons. We're introducing this kind of dense matrices to represent a fully connected architecture. And then in the convolution also, we went from a single convolutional neuron to multiple convolutional neurons, in other words, multiple filters. And so that's exactly what we will do now here. We will we need to do that for yet another reason. It's very unlikely that all our applications will actually require a scalar output. Okay, so this specific application, linear regression, sorry, not regression, the regression problem was requiring, if you like, a scalar output, but obviously other problems will not. So somehow we need to produce, we need to accommodate two things. The first is that that kind of state that we have produced the prediction out of, it in general has to be a vector. And actually we can see that even in this simple regression kind of problem, y itself has to be a vector. So we are introducing now some form of decoupling. So let me write this down so we kind of have it in writing. So we need to do two things. So we need to increase the number of parameters, meters associated with our model. That's one thing. Secondly, we need to make the hidden, let me call it hidden state, h of t a vector, therefore h underbar of t, and decouple it from the dimensionality of the target variable. Why? Okay, so this is kind of quite important even in this kind of problem. So we don't have necessarily in this problem to have just a single neuron with just 3 parameters. We can actually have, as we will see, a simple RNN layer now that consists of multiple of these neurons. And we'll see exactly how we will construct it. And produce, if you like, a vector state H50 at or a vector state ht in general at every single step. And out of this vector state, we can do dimensionality matching as we have done in every head that we have seen in earlier kind of neural networks in order for us to match the dimensionality of our predicted variable, which is the y, the target variable y. And that's why I was actually drawing these kind of arrows from each of these stages a bit later, a bit earlier. So another way of actually thinking about it is that vector hidden state will capture all of the dependencies that a price will actually have, all these hidden latent factors that the price will depend on. It could be a season, could be some sort of values that are preceding, if you like, this specific trading day. For example, the fact that we have a trend over here. Therefore, the price of this trading day may be dependent in with let's say a number of early trading days, but definitely will have not a lot of dependency on this one. So the size of this, the dimensionality of this hidden state, is itself our own kind of design variable. So it has to be an architectural kind of parameter that we need to keep in mind, and how to sort of select it. Just like anything that we have seen in the past, every single neural network will have that kind of problem at hand, and how many neurons we need, and so on. Okay, so what we will do now is we will draw that kind of architecture, which is the generalization of this simple neuron that we'll call now the simple RNN layer. And I maintain the term simple because we will see that this is one of the two main architectures we will be dealing with on that of RNN type. Right now, we are dealing with the simple version. So let me just draw it. So we will, in the input, we're going to have some kind of concatenation of a hidden state, which is now a vector, and the input x of t. In general, this input will be a vector. In our problem that we have seen in time series was a scalar, but in general will be a vector too. And by now we have seen in early videos that we have this matrix that we multiply with the concatenated kind of vector W. We add the bias B, and we pass it through the nonlinearity tan H. Now every single nonlinearity we have seen in the past was also vector in vector output function, so this does not change anything. So we can just maintain that for tan H as well. Okay, so this is our vector H of t. And similar to what we have seen earlier, we will be passing it through the D, and we will be, D is a memory location, so we will be storing this vector and then retrieve the, actually this is HT minus 1, retrieve the earlier hidden state and feed it to the input. As we will see, we don't have the multiplication that we explicitly drawn here because there will be, the equation will be slightly different. And there will be a multiplication for sure with this hidden state. It's just not shown here. And so that will be that is the what is called a simple RNN layer. So let's write down some kind of the equation that represents that vector hidden state, and see how it is also related to the fully connected layer that we have seen earlier. So the equation generally is going to be h of t. The vector is going to be tan h of. So we will be introducing here a matrix U. This matrix U, I'll draw it like this, is going to have n input. So always n was the kind of dimensionality of features in terms of x. So right now this n is decorated with input, just to distinguish that from, and then we'll have n neurons as rows. So n neurons is the dimensionality of h of t. So it is n neurons by 1. That is the dimensionality of h of t. So u will be multiplied with x of t, obviously, because it refers to the input. Okay, so x of t is a column vector of n input rows. Let me actually write it over here, the dimensionality of x of t, n input by 1. So that's the input. And this is now a plus sign, plus, and we're going to have a W prime matrix. This matrix W prime will be n neurons by n input, and it will multiply this h of t minus 1 state. Okay, and we'll see this W prime matrix is embedded in this matrix W. That's why the thing is missing from here. Okay, so this is evidently h t minus 1 has exactly the same dimensions as h of t, plus b, which of course b is n neurons by 1. And this is the closing of the parenthesis. So the only thing that remains is to define this W matrix, which is the concatenation of U transpose and W prime transpose. So the dimensions are work out because U transpose is it is n neurons by it is n input by n neurons, and the WT transpose is still n input by n neurons. So the dimensions of W is, and I have done a mistake over here, this is n neurons by n neurons. So the dimensions of W prime transpose is n neurons by neurons. So finally the dimensions W is n input plus n neurons by n neurons. Okay, that's basically it. With this dimensioning, effectively we can write this equation as exactly what the block diagram kind of indicates. Tan h of, with this dimensioning we have the concatenation of xt and ht minus 1, left multiplying the matrix W plus B. Okay, and this is basically our equation of a simple RNN layer. And then we have the contrast this against the sort of fully connected layer. The fully connected layer is, let me write it here, is, we have seen earlier, is Z of ReLU of WX plus B. So you can actually see how the two are kind of contrasting. This is the fully connected layer, and this is the RNN, the simple RNN layer. So this is now part of the story. The decoupling has also to be implemented. So at least we reach a point where we have now a vector h of t and increase the number of parameters, as we'll see, significantly. And therefore we are able to model more complicated hypotheses. The decoupling needs also to be outlined. So what we will actually have here, we're going to take, so we need to implement, as we discussed, the decoupling between the hidden state and the dimensionality of that sort of target variable y. And therefore, this is going to be done exactly as we have done in other network heads by some kind of fully connected layer, V I will call it, that it will take this h of t with the dimensions, as we discussed, of n neurons by 1. by 1. And using the matrix as a transformation with some bias C will give us the output, let me call it O of t. Obviously not 0, just a letter O. Okay, and this is going to lead us to implement a variety of tasks. Depending on the task, we may have a softmax. As we have seen in another video, what the softmax is for classification, multi-class classification problems. Let me write down as classification. And or we may actually see it in the case of regression, implementing some form of linear unit. Let me call this, I don't know, E as a vector. So E transpose O of t will give us a y hat of t, and this will be the regression case. So as a couple of examples, well, starting from our current example we have right now, we may have a hidden state which is, let's say, 20 or 30 or whatever dimensions, right? So in terms of n neurons will be 20 or 30, because we believe that 20 or 30 different latent factors are affecting the price of the asset of the commodity in the next trading day. And then evidently we will need to match 20 with to 1, okay? And this is effectively this dot product, and this will implement our regression. That's our example for regression. In the case of classification, we may have a hidden state over here, let's say of 100 or 300, and we need to be able to match it with the number of classes that we have here. So this matrix V is going to match the size of the hidden state to the number of classes that we need over here, which is effectively the same in terms of dimensions of the input of the softmax. So we need a posterior probability distribution, let's say, of k, of size k. Sometimes this k will be small, sometimes it will be quite substantial. In the case of, for example, of language modeling, we have to predict the next word that is actually going to happen, given, if you like, a model that is going to be of some kind of, has some kind of form of memory. And this will be potentially in the millions. Okay, so this matrix V is not necessarily doing dimensionality reduction. It may need to expand in terms of number of dimensions and therefore matching the dimensionality of h of t to whatever number of dimensions we require, again, for multi-class classification. To close a video discussion about the architecture of a simple RNN, I think it's worthwhile discussing a little bit another enhancement that we also have seen in earlier architecture, the so-called deep RNNs. So instead of having just a single layer, we were going to have multiple stacked layers. And the rationale of that, so let me just draw that kind of architecture. So we're going to have a simple RNN layer, which I'll call RNN1, that is going to sort of receive a state xt minus 1, xt minus 1, and then it's going to obviously receive from an earlier instance an ht minus 2, which is of course a vector now, and it will return the ht minus 1 for the first layer over here to another unrolled, of course, instance of that RNN, which will receive an h of t, and so on and so on. This is the first layer. But now, instead of just matching the h of t minus 1 dimension into a certain output, which happens over here, we are actually feeding this h of t minus 1 into another layer, another simple RNN layer. So I will call this RNN2. And this layer is actually operating in a similar fashion to the first layer. So it itself has its own kind of hidden state, ht minus 1 of 2, and so on and so on. And therefore, finally, we may get a number of layers. And in fact, what we can also do is we will be adjusting the dimensionality of this hidden state per layer now. And it's again our own responsibility of what kind of dimensionality is. So each layer may have its own dimensionality with respect to the hidden state. So let me put underbars here to keep that in mind. And finally, when we are all said and done, we will be also implementing at the end the head. And this head may be, as we will see in some applications, will need to be implemented and exercised at every step. But in some other applications, it may be exercised only at the end. So let's say in sentiment analysis, an application that we will see in the natural language processing kind of video, we will only need to produce a prediction at the very end of accepting, let's say, a sequence of text, because it doesn't really make sense to predict something when you just read a couple of words. So you have to read the whole, let's say, product review before you determine whether it's a positive or negative review. Okay, so that's one example of exercising this head at the end of this kind of processing. And now let's see what happens in terms of going back to this notebook and see one instance of this deep RNN specifically for the regression problem that we have dealt, the time series prediction problem. So this is the notebook. We are effectively matching, we have 3 layers. First layer with 20 neurons, second layer with another 20 neurons, and then the third layer with a 1 neuron. And every layer is sort of accepting the dimensionality of the hidden state of the earlier layer. The rationale of having that is evidently to gradually build somehow the representations that we need in order to make the final prediction. In this case, we are using the simple RNN layer itself to create the scalar output. We could have used a slightly different architecture where we use these kind of fully connected layers to do the dimensionality matching. But in this case, the author decided to do so. So the deep RNN evidently will have better performance than what we have seen earlier in terms of the prediction ability. Not only we have introduced in this case what we have seen earlier, more neurons, but we also introduced multiple layers. So we significantly increased the number of parameters that we need and kind of matched the parameters we have with those that we have seen earlier in the fully connected architecture in the so-called baseline case. This second case is actually shown here, where we have now a matrix V matching the dimensionality of the hidden state delivered to us by the previous layer, the previous simple RNN layer, and delivering to us evidently a scalar. And this is actually the architecture that performs very, very well in terms of our prediction.